Hello there. Welcome to a problem session. So this is a problem, very standard problem. It's in many books. In particular, it is in a variation of this problem is in Kleppner and Cole and Co. I really like that book. So if you get a chance and get it, so I'll just write it down. Kleppner and Cole and Co. Okay, so there they have a car in which a pendulum is swinging, and the car is accelerating at some acceleration a. So if there's no acceleration, if a is 0, so this pendulum will swing around this equilibrium. So it will have some maximum angle theta 0, and on the other side be same theta 0. So it's going to move from this point to that point and come back, right? Now when it's accelerating, the question is what will happen, and we're going to do it for small angles. And what small angles means for us is that whenever I see sine theta, I'll be able to replace with theta. Whenever cosine theta, I'll replace with this. These are like a Taylor expansions. This approximation from Taylor approximation, expansion of sines and cosine. And we'll further do is in any formula we find theta squared competing with theta, we can just drop this. If I have something like this, I just drop this compared to theta. Something like this, I drop this with theta. So, so these guys will be all dropped, and only linear in theta. So linear in theta, if I have a theta dot, theta double dot, those are things that will survive. Okay. All right. So how do we proceed it? You know that the laws of motion is for this one body, for m, the motion will be completely dictated by F equals mass times acceleration at an arbitrary instant t. So that's the equation of motion. But it's only true in inertial frame. Right? Now, if you use to study, say you're inside the truck and you want to study this this coordinate system fixed to the truck, that will not inertial frame. This is not going to be the law for it. That's not inertial frame. So for non-inertial frame, you'll have to do F of t plus fictitious force, which may also depends on time. But here we're gonna just say that depends on this, and we're keeping it that uniformly accelerating truck. So that could be changing with time, but not for us. This is equals to mass times acceleration in non-inertial frame. And the formula for this is for one body like m minus m times the acceleration of the frame itself, which happened to be this. Okay. When we do this, it'll turn out to be much easier to set this up, all right, than that formula. So we're going to try to do it using this. All right, so let's think about how do we know. So this acceleration of the frame is that way. So this acts like there's a force that way, even if it's at that point. If you at this point in time, at t equal to 0, it looks like You have a gravity, you have a tension, and then you're going to have a mass times A pointed that way. This is the fictitious force. At this point, there will be an acceleration pointed, that acceleration of this mass will be that way. But if you want to get equation of motion, you don't look at a particular time, you look at some arbitrary time. You can see that at some time this will be pulled, this acceleration even has zero velocity, at very next instant is going to move on this side, move to this side, move to that side, to the left, right, in this picture. So what's going to happen is at arbitrary time we can say this is the vertical and it's going to point to some point over here. So this angle will be theta of t, and we'll point x-axis that way, just, and these are all, this x-axis in the last video I used primed, but I'm going to drop that now, and this with the O. So you can maybe you can even do something like this. You can do x this way and the y this way. So this whole thing is in the first quadrant. It's up to us to choose this, right? So we will be using polar coordinate anyway because it's a polar coordinate problem. Okay, so here at this time is this polar coordinate theta of t, and from here to here this polar coordinate r of t. So it's some arbitrary instance like that. And if now you look at what the force structure is, force is down like that, and ma is that way, and tension is function of time. We don't know what the tension is. Tension is whatever going to be Newton's law. So it's going to be in a circle like that. You can see the radial vector is that way, unit vector, and the theta vector is that way in this coordinate towards the y-axis. If you remember, in the polar coordinates x and y, for this point radial vector is that way and angular vector is towards the y-axis from the y-axis in the first quadrant. It's good to remember a picture like that because you want to use it everywhere and you don't have to worry about the sign and things like that. If you don't put in the first quadrant, chances are very high that you are going to get some kind of error. Okay, so in the radial coordinate, this equation will be one along the r direction, so r hat equation, and then you can have a theta hat equation. So just like x equation, y axis in the radial coordinate, it will be like that. So when you look at this, tension is all in the radial direction, pointed in the opposite to the radial direction. So one of the forces going to be tension, and these guys will have both radial and tangential. So this mg, if you look at this is theta, so this is theta, so the mg cosine theta will be radial direction. This is minus plus mg cosine theta. So I'm going to make this simplification later, but right now write in cosine theta. And how about this guy? So this is theta, then this is 90 minus theta, then this is theta. So this is this would be sine theta, and it's going to be the positive side, plus mg, not mg, ma sine theta. A is the acceleration of the frame itself. Okay. On the other side is going to be mass times a sub r. Now you might remember that a sub r equals to r 2 time derivatives, this 2 times that minus r theta dot square. So this will be m r double dot minus r theta dot square. And you can later on we'll see that r dot is not changing with time, so this will be go to 0, and this r will be, let's say, L or the pendulum, so this will become L, and so this will simplify to that. And when we use theta dot square much less than theta, like theta square much less than this theta, this term will go to 0. So when we go to small angle, this will become minus t, and this will become mg, and this will become plus ma theta, and the right side will become 0. So pretty cool, right? So this is the equation we will deal with later. So let me erase it and look at what the theta hat equation look like. Okay, so theta hat equation will be same forces, so I need to work out, there will be tension has a 0, tension was all along the r hat, so for theta hat I will have both for mg, this is theta, this is angle theta, so it's going to project in the opposite direction theta hat, so it's going to be minus mg sine theta, and it's going to be for ma is point this way, so it's going to be plus ma cosine theta, and on the other side, is going to be theta, it's going to be mass times a theta component, and a theta I wrote down earlier is as this from the polar coordinate perspective, so r theta double dot plus 2 r dot theta dot. Now r equals to L, then r dot equal to 0, so you can see the this thing is 0, and so this just becomes ml theta double dot. And on the left side, for a small angle, this will become minus mg theta, and this will be plus ma, because theta square will be dropped. So this for a small angle. So these are two equations that our equations of motion. To find equilibrium point, so it's going to be swing. It won't be swinging about this like that. It's going to be swinging about some other direction, because this was at rest, and when it goes up there, somewhere it's going to be at rest. So it's going to be swinging back and forth. There is no way it's going to make past this, because this is already at rest, and the force at that point is pointed to the left. So there will be no motion to the right of this. No motion here on this side. So motion is only back and forth over here. So let's see this angle at which is going to be somewhere, some angle here. Let's see some angle here about which is going to swing around. This angle will be equilibrium angle, means the forces will be balanced here, right? So at that point, acceleration will have to be 0, and so at that point, the equilibrium point, so from this I have mg theta bar plus ma equal to 0, and so theta bar equals to, bring this go, pause it, so it's going to be a over G. So if we want to have angle with respect to this reference, so let's call that angle phi. Okay, angle phi. So with respect to reference to equilibrium, we define angle, say phi equals to theta minus theta bar. Then phi dot equals just theta dot, because this is constant. Phi double dot equals to theta double dot. Now when you use this, okay, so for this angle, so we are trying to describe motion like that. So that's the angle, the right correct angle. Now using this into equation 2, convert that into phi. That will be minus mg. Theta equals to phi over theta, phi plus theta bar. I really don't need to do this much simplification, but I just wanted to make sure this you can see it. You can see all the m's go away, and g theta bar is going to be a. G theta bar is a, so this term cancels out with that. So we have a minus g phi equals to g over L phi equals to phi double dot. And this simple harmonic equation is, you have phi of t equals to a cosine omega t plus b sine omega t, and omega equals to square root of g over L. Kind of, that will be the solution. What's given is when theta is 0, when theta was 0, t equal to 0, theta equal to 0, theta dot is 0. This means phi dot is 0. And so t equals 0, phi dot is 0. You can see phi dot here. That will be minus omega a sine omega t plus omega b cosine omega t. So if you say phi dot at 0, that should be 0, and you put 0, that goes to 0, and this just omega b. That means omega not equal to 0 means b equal to 0. So you don't even have that, so you just have this because of this initial condition. So just need to figure out what a will be. So at t equal to 0, what's the phi? Theta is 0, so then phi is equal to 0 minus theta bar, right? So it's minus theta bar. So let's see, at minus theta bar equals to a times 1 at t equal to 0. So a is minus theta bar. So phi of t is simply minus theta bar cosine omega t. So that's the solution, which tells us how in time is going to go back and forth. And this is a complete solution because everything is known here. We want to write in terms of angle theta. All you have to do is theta t will be, I think phi is equal to whatever the theta is minus theta bar, right? Theta minus theta bar. So that's yeah, theta minus theta bar. Yeah, I noticed a little sign error here. This angle should be labeled as minus phi of theta, because you can see phi plus theta bar is theta. So if I have a theta bar at this angle, then you get theta. Okay. Okay, so algebraically it's still sound. So theta is equal to theta bar plus phi. So just you can say theta bar 1 minus cosine omega t, which is theta bar is a over g, 1 minus cosine omega square root of g over l t. So that tells us angle from the vertical. This is the angle vertical with time, and it's the complete answer. Okay, this is a pretty interesting problem. It shows the power of using accelerating frame equation when that's the most convenient one to use. Tomorrow in the next video I'm going to do acceleration of the frame when the frame is rotating. Now this frame was all translating. It's very easy to do, very straightforward. All the examples we have done, you say, hey, this is, I could have done some other way. It's true. But when the frame is rotating, it turns out acceleration is a little bit more complicated to figure out. So we're going to figure out the acceleration of the frame that's rotating with respect to inertial frame. So see you then. You can meanwhile you can check out my website, and you can hit the like button or subscribe to this channel. Helps distribute this information to more people. Okay, take care. Bye.